So, hello, welcome to my talk. My name is Florian Habermann. I'm one of the co-founders of the MicroStream company, which is behind the MicroStream framework, which was released in the public only last year. The framework itself is it's battle tested for 6 years in large projects, and we decided to make a product out of it, and last year finally we released it for the public. It's free to use, and we are finally found a way to go open source actually, but more to that later on. It is a persistence and data streaming framework. In this talk I will cover the persistence part, in-memory database stuff, which can be done with the framework, and on Thursday I have another talk. There I will cover the data streaming or serialization capabilities of our framework. So, little legal stuff which I have to show. Part of my talk now, it's a rationale behind the framework, why another persistence framework, what's the idea behind it, how to install it. It's just a framework, so it's the easy part. And then we cover the starter configuration and the life cycle of the storage engine, how to load data, how to cover eager lazy loading, stuff like that. How to store data, the type mapping, what happens if my classes change, if my data has to be refactored, how do I handle that type of stuff, and the backup at least. So nowadays, how is data persisted? You have the application with a JVM or a microservice or part of a huge cluster. Every time it's a JVM which runs the application or part of the application. And inside your Java application, you have the objects as a graph, logically. And every storage technology out there has a different schema. So you have the old relational databases, which have tables, or the new SQL generation of databases, which have key value, document, graph, column store, stuff like that. Everything is not compatible to the Java object graph. So every time you want to store or load data from the storage system, the external storage system, you have to map your data to convert the data, and that's expensive. And it's a huge overhead to do, and it brings a lot of complexity to your application, and it's a source of errors. It's doable, most systems run with it, but we always thought there must be a more elegant way to solve it. So what we came up with is probably, it looks the same, but we got rid of the conversion of the data, because we treat the object graph as it is and store it as it is in our storage layer. So you don't have to worry about converting your data. You don't have to take care of querying the data with some third-party query languages like SQL or whatever is out there. And you can concentrate on developing your application and not you don't have to worry about a lot of external stuff, managing caches, transactions, and connection pools and stuff like that. So what we do is we developed a very new from scratch up a serialization engine. That's the base of everything. And the serialization engine can serialize or deserialize parts of object graphs and restore objects in memory and bring it back to life in your live object graph. That's a key difference between the existing serialization engines out there and the MicroStream serialization engine. So if you have a live object graph and load data from an external source, the objects can be integrated or reintegrated in the existing graph. And this is done under the hood by the engine fully automatically. So that's a key difference to all other database systems. So probably you can say it's a kind of a paradigm change. The source of truth isn't the external storage layer anymore, but your application itself. And when you store data, it's just more like a backup or insurance that your data will be secure on the application exit. Where you store your data doesn't matter. We can store or stream to all systems which can handle binaries. So that's a new feature of the version 4, which was released 4 weeks ago. Before version 4, we could only write to the file system, but now we abstracted the storage handling, the byte handling. Now we can write to any system which can handle bytes or blobs. So the most commonly used thing will be, I guess, blob storages in the cloud provider environments like S3, stuff like that. We can write into distributed caches in memory data grids, even to old relational databases. So pretty much everything which can handle bytes. So you can get on high available storage layer as well, if you like so. So since you don't have the performance loss through the conversion or data mapping, the only thing which is performance relevant is your Java application, and Java is fast. You can leverage the full performance of the Java virtual machine, and you don't have to rely on an external storage layer anymore. You don't have the network bottlenecks, for example, which can cost a lot of time. You don't have caches or conversion from the data out of caches and stuff like that. You just use your object graph as it is in your Java application, store and load it, and that's just a few lines of code you have to do. I will show you later on. All right. So MicroStream is just a Java library which can be installed via Maven. Currently, we have it in our own repository. Just add the repository tag to your Maven configuration or Gradle or whatever you want to use. And the storage embedded artifact is the core of the storage engine. Like I said, we are about to go open source. It's a matter of months, I guess. And then we can distribute our libraries over the Maven Central or other repositories as well. The main class to connect your object graph to the managed storage layer is called Embedded Storage Manager, just called the start method, and you've got a fully fledged up and running manager. With the shutdown, you end the lifecycle. That's all you have to do. Shutdown isn't even mandatory because all threads or all actions which run inside threads and return are done. Or if you call a store and the store method returns, your data is safe, so you don't even have to call the shutdown. But it's a a good practice. When you start something, then you can then you stop something as well. So actually, the storage manager is just set up with all kinds of defaults or user-defined settings and definitions. What is actually started are the database managing threads that process storing and loading requests. The requests are handled either by you, if you want to store data, and if you want to load data, the requests are handled automatically because the engine does the loading in the background, so you don't have to worry about querying data and stuff like that. The storage, embedded storage start convenience methods are overloaded with the most commonly used parameters. For example, the root object, which is the root of a persisted object graph of the application, can be handled as well, and the storage directory where the data should be stored. In this case, it's just a local file system, but you, like I said, you can use different storage targets as well, for example, blob storages in cloud environments. And that's all you have to do to connect the root of an object graph, which should be persisted, to the storage manager. A more complex example would be the storage manager created by a so-called foundation. These foundation objects are kind of factory objects which can be polluted or configured with different kinds of configuration aspects, and then you can create the storage manager out of it. It's one way to configure the storage engine. The other way is external configuration, which will be next. So here we can see you use a storage channel provider, which says 4 channels should be used. A channel is basically one thread in the application, which is connected to one channel in the storage, maybe one bucket in Amazon S3 or one folder on the directory. So you can parallelize your storage and store and load operations. And there we see a small backup setup, which ensures an incremental backup in another path of the file system. You can, for example, split the live and the backup file system. That you can that you have the live file system, for example, is on your local disk, and the backup system is in a remote storage. That can be done as well. So, like you can see the framework itself, it's highly configurable. Everything's, the architecture is interface based, everything's an interface first. So if you want to change a little bit of the engine, of the behavior, stuff like that, it can be done easily. Going over the foundation classes, just configure your engine like you want to and start it up. Later on, we will see a few more examples how to configure a few parts or control behavior of the storage engine. If you want to use external configuration, it can be done as well. Just use a storage embedded configuration artifact, and then you can access the configuration API, which is kind of a key value API. So you have simple setters to set parameters, and in the background, the appropriate classes are created as well. So this is done per code. And if you will want to use externalized configuration, you can use the loader methods to load resources which contain the configuration externalized. Currently, we support XML and property files or ini files. Yeah, most developers know it has usage for profiles like development, test, and production system. Or if you're just a fan of externalized configuration, you can use it as well. So how is loading data done? The old way is to use a data layer which accesses the data storage or the storage layer, probably about DAO objects and stuff like that. You have to use queries or use a query framework like the JPA criteria and stuff like that. You have to put plain strings in your Java code. You have to learn new APIs. It's always a bit of a hassle. You can make errors and complex queries. If you want to join a lot of data, you have complex data you want to load. It's always a lot of querying you have to do by yourself. How is it done with MicroStream? You just say start your storage, and if the storage root is null, then you can inject a new root and store it. If a root is already there, the engine loads it on demand at startup fully automatic, so you don't have to query stuff. The default behavior is eager loading, so everything which is reachable from the root will be loaded into memory. And if you have a lot of data, probably in most projects, you will have more data than a RAM available at the machine. You can define lazy loading points, what data is loaded later on or on demand. But this is, I'll show you later on it in the presentation. So basically, everything is loaded at startup. You don't have to manage the loading. How is it done, or how is it done? But you have to define lazy loading points that you don't pollute your memory or get out of memory errors. So the lazy loading, how is it done? For example, you have a business application. There's a map from which has the year as key and the business year object as values. And the business year class has all turnovers, all revenue, which is made in this whole business year. And that may be a problem. If you have a big company, a big shop, stuff like that, you have a lot of turnovers, a lot of transactions which will be stored per year. And if the business is running for 5 generations, you will get a problem from data-wise from the size and the RAM at the start. So we have to call the engine that at this point it should be loaded lazily. All you have to do is to put a lazy before your list. And if you load or if you access this lazy object, you don't have to form some query like select stuff from turnovers where ID is whatever. The engine just does it in the background for you. You don't have to worry about anything. So sorry for that. Yeah, just call the get from the lazy object and you get your turnovers, and the loading is done in the background. So a lot of people ask why we don't, why we have to write lazy before that. Why don't we use annotations like JPA does, for example? That's our approach to that is we just want to provide an API. It's a pure Java library without any dependencies to third-party libraries, and we don't want to do any middleware layer, middleware intermediate stuff like bytecode manipulation, like Hibernate does. So if you would have solved it with annotations, we would have to do some kind of bytecode manipulation to control the data and stuff like that. So our approach was to keep it simple and API only, without annotations or intermediate magic. So it stays debuggable, and you're more in control of what happens in the background, and your classes stay the same. We don't manipulate bytecode or stuff like that, or use our own collection classes to get the handling done, like in JPA or Hibernate. So to create a lazy reference, you say lazy reference, hand over data, null or just null. Doesn't matter how you define it. And the boilerplate code would look like this in a getter. If you want to access the turnovers, you have the lazy object wrapped around. So you have to ask if is turnovers null, then null, or else you could access the turnovers list. But this is a bit clumsy, so we just introduced the lazy get, and you're good to go. Just say lazy get is turnovers. If turnovers is null, you get null. Otherwise, the lazy part is loaded in the background, or the content behind the lazy part is loaded in the background for you. Yeah, I covered that already. We don't use annotations for that because it would be a hassle at runtime, and we don't want to use bytecode manipulation of any sort to get that stuff working. So a complete example would look like this. You have a field which is lazy. The getter just says lazy get, and the setter just accesses or assigns a new lazy reference to the local field. So this is encapsulated in your business object. The caller of the business here methods doesn't see that this is lazy or lazy loaded. And that's the best way to design it. You encapsulate your loading inside your business models, and the caller isn't bothered with stuff like lazy loading and validation, stuff like that. A few more methods for lazy loading are lazy get peak, meaning you can check if the data behind lazy is loaded. And lazy clear removes the content or the referenced objects from the lazy out of the memory, but the persistent state is kept. So you can free the memory at runtime if you run out of memory or your memory gets a bit sparse. But you don't have to do it manually all the time. It would be a hassle to keep monitoring the size of the remaining memory. So we have a lazy reference manager for that, which can be populated with a few predicates or stuff like that. And the default behavior would be that all lazy references which are not touched for 30 minutes or a certain amount of time are cleared, or if the memory quota exceeds a certain value. For example, if only 25% of the memory are remaining, then the lazy reference manager gets active and clears the oldest untouched lazy references out of the memory. But the persistent state will be kept and you don't lose any data. And just on the next get call of the lazy references, it will be loaded again into memory. So the more interesting part, how do I store data? Basically, every time you change an object, you have to store it like everywhere else. just store the storage manager. If you have assigned a new root object, just call store root. If you change a single object, for example, you update some properties, just store this single object. And if you change a collection, if you add an object or remove an object from a collection, you're actually changing the collection itself, so you have to store the collection. But don't worry, we don't write the whole collection again, just the references, and if some new or changed objects are inside this list, they get stored, and that's it. So you can have collections with millions of entities, and you can call the store method without any performance overhead, or there are not a lot of data written. This is handled by the engine internally. That only objects are stored which are actually have changed. If you want to store in batch, kind of like a transaction, you can use store all methods, and all objects which are given as parameters are stored in a batch operation or single transaction, and it's all or nothing operation. So if the store all returns, the data is stored successfully, and if something goes wrong, maybe a network problem or out of memory of some sort, the data is reverted to the last known stored state. So you cannot corrupt your data if some I/O error occurs or stuff like that. The engine takes care of that with transaction monitoring. And if some corrupt data was written, then the data pointer or the transaction log with this, which is kept in the background, won't update. So your data doesn't corrupt in any sort. If you have calculated fields or fields you don't wanna store inside your object tree, just use a transient keyword. Everything which is transient is not stored, is not part of the persisted data. If you don't want to use the transient keyword for this, for example, you can use a naming pattern. Everything which starts with an underscore isn't persisted by the engine. Just use a persistence field evaluator and hand it over to the foundation classes like I showed at the beginning. Then you can handle how the fields are evaluated or stored or not. And this is one of the many things you can control in the life cycle of the application. This was the lazy storing. The lazy storing checks one object or all references of this single object and stores the changed stuff. So if you want to store everything which is reachable by a certain object, then you can use the eager storer, and the store method stores everything which is reached by or referenced by this MyData or the handed over references, and then you can store everything in a batch operation as well. So you can decide if you want to use a lazy storer or an eager storer. That's two things we can we provide. If you want some different storing behavior, you can implement it as well and hand it over to the storage manager. If you want to control which fields are stored eager or lazy, You can do this with a persistence eager storing field evaluator, which says which fields should be handled eagerly every time. For example, with a naming pattern or stuff like that, or maybe with another Java modifier, which you can use for that. In this case, if a field starts with an underline, it is stored every time the referencing object is stored as well. So you can ensure that referenced data is stored if a referencing object is stored as well. So you can design your application that the storer calls an outside object. For example, you have a purchase. A purchase consists of items, and you don't have to worry about storing items if the item is all stored eagerly. So just store the whole purchase object, and the items are updated as well, for example. Yeah, these are the two ways to control eager storing. The store in combination with the field evaluator or the eager storer itself. How is data deleted? In databases, you call delete from, stuff like that. How is it done in Java? An object is deleted by the garbage collector if it isn't reachable anymore. That's how MicroStream works as well. You just remove items from the referencing objects and store the object itself, probably a collection or a reference inside in a field. That's how deleting data is done in MicroStream, just like in Java itself. We do a lot of housekeeping in the background, for example, the file or storage layer cleanup, because every time an object isn't reachable anymore, it has to be removed from the storage as well. So we have kind of a garbage collector which watches this, the data layer and keeps cleaning up the data layer in the background, so the storage files won't be grow out of place. You have a cache cleanup for the local cache we use in the background for the binary data, and the garbage collection as mentioned. And depending on how often you update your object graph, if you have write-heavy applications, you should probably configure the housekeeping controller with a bigger budget, and so you can stay in control or configure how much time the controller has to do the cleanup and stuff like that. If you have a read-heavy application, then the housekeeping controller should be fine with the standard settings. That's the default settings. There are a few more stuff which can be called: cache checks, file checks, garbage collection, and so on. They can be called manually if you want to have the evaluation controlled by your application. But in most cases, the default stuff will be sufficient. One of the most asked questions is, what do I do if my classes change? Do I have to rewrite my storage? Do I have to refactor stuff, or how is it handled? For example, the contact type have a few moved fields or renamed fields, new fields, stuff like that. In MicroStream, we call it legacy type mapping, because if you have stored versions of the left contact class or contact objects, and you start up the new deployed application with the right version of the contact class, the thing MicroStream does, it converts data on demand. It doesn't rewrite the whole storage layer. This would be too much if you have a lot of giga or even terabytes of data. But it converts it on demand to the new version of the class. The most common cases are detected by the engine. It's a heuristic which runs in the background, but if you have more complex cases, you can declare a mapping which should be done, and you're good to go. Yeah, that's a console output when field changes or class changes are detected. And you can provide a mapping either via API or with external files. Then you can say what fields got changed, what fields got updated, removed, and stuff like that. Short note on the backup. We have, per default, we have an incremental backup running in the background. But that was covered in the early example of the configuration layer. All right. So, like I said, we are about to go open source, and we have a GitHub site already. There are a lot of examples, a fully fledged example application. It's a Spring Boot application with a little UI layer as well, and there you can take a first peek. How do I set up my application to work with MicroStream? For example, you can see there that you don't have to use any annotations or special interfaces, or you don't have to extend a special super type from us, just use your classes as they are, and MicroStream is able to persist them as well. Documentation and stuff like that, just go and visit microstream.one. There you have the links for the getting started and stuff like that. If you're interested how the serializing behind it works, or where we go, what different features we have, you can visit my talk on Thursday, depending the serialization part or the data transferring part of MicroStream as well. So if you have any questions, we still got a little time for that.
I have a question. What about distribution? Can I use the database from different nodes, or is it just one node where I can query and update things?
Yeah, currently the connection is one-to-one, one storage for one Java virtual machine. We are currently working on a distributed system which can handle distributed applications. What we have done in existing projects is we used data grids to communicate between nodes, and the persistence layer was done by MicroStream, for example. This is done in a few applications or customer projects out there, but we will come up with an automated part of that, so you can distribute your object graph over several nodes or JVMs. Yeah.
Sounds good. One last question. Why is it faster? Serialization is some kind of mapping too. Why is it so much faster than, for example, Hibernate mapping or JPA?
Because the creation of the objects is done in a special way. So we are even faster than the Java serialization, the inbuilt serialization, up to 10 or 20 times. And if you compare the querying databases, putting data into caches, the object mapping itself, the object relation and mapping itself, that's the expensive part in most applications. Okay. And that's where we gain our performance, because we we have an object relation mapping in the background. Also, we know every time which objects are stored in which part of the storage the objects are, and we can access the storage randomly. directly. So we don't have to query huge sets of data to gather all of the data we want, because due to the serialization process, we know exactly which internal IDs the objects have and where they are stored in the storage layer. So the whole database of the storage layer is indexed fully by default. So you don't have to worry about stuff like that as well.
Okay, thanks a lot.
All right. So just go over the questions. There are quite a few. So, yeah, this question, like data can only be properly accessed by Java application. For example, the item would only get data from application. That's true. But the data can be accessed by external systems as well via REST. We have an REST API, or you can use any other default accessing stuff to get on your data. Probably most of the time we do it by REST itself. We have an API for that, or you just start on REST server out of your application, and your BI tools can access the underlying data as well. So you don't have to define REST methods because it is done by the framework. We have done it with a few BI servers in applications. It's a bit different because the application doesn't connect to the database, but to the application. That's the main difference, but it will be able to access data as well to get an API done. PostgreSQL can be used as storage target. Currently, the first the release 4 has connections to everything Oracle offers, from Oracle Coherence to Oracle Cloud. But the next releases, we have a plain SQL or an interface to all SQL databases. Then you can use dialects for that as well, and to other vendors as well. So PostgreSQL will be there in the future. So thank you, and have fun at the JCON. See you.